All right, everybody, welcome back. I don't think the system time has flipped over to 11:20 exactly yet, but we have Kirby Runyon up next. He's going to be talking about interstellar probe and flybys of objects in the outer solar system. And I believe, Kirby, yes, you're going to share your own slides for now?
That's right. Can you hear me?
I sure can.
Excellent.
Take it away. It's all yours.
All right. Thank you, Michael. So glad to have you all join us today. I'll be talking about opportunities for planetary flybys from interstellar probe. Now, of course, the primary goal is heliophysics, understanding our habitable astrosphere and its home within the galaxy. But beyond this baseline mission, there are possibilities for augmented versions of this as we present a menu of items to the Heliophysics Decadal Survey panel. And those are planetary science and astrophysics. And while Mike Zemkov will be speaking next on possible astrophysics opportunities from interstellar probe, I will be speaking on planetary science, specifically looking at the evolution of planetary systems. Now, I know a conference like this tends to attract a lot of space physicists, heliophysicists. Just by way of a little bit of background here, of course, there we go. Our solar system has a handful of terrestrial planets, a handful of giant planets, but over 130 dwarf planets. Overwhelmingly, dwarf planets are the most common type of planet in our solar system, and yet arguably they are the least understood. And so, and I'm defining a dwarf planet here as a body 400 kilometers in diameter up to about Pluto sized. And so they're the most common type of planet, and yet they're the least explored. And so, New Horizons really led the way here, showing us Pluto, just as how New Horizons surprised us with a very active Pluto with an impressive ice mountains floating in oceans of nitrogen ice and a very unexpected oblate contact binary 2014 MU69 or Arrokoth. A flyby of another planetesimal or dwarf planet will bring completely new discoveries and answer questions that we're not even smart enough to ask. There are over 4,000 planetesimals and 130 dwarf planets out there in the Kuiper Belt. So the exploration of the solar system is still really in its infancy. Planetesimals like Arrokoth have not been altered much since they were created 4.5 billion years ago, and they're therefore a sort of fossil record of solar system formation. The dwarf planets, on the other hand, teach us about the freezing of ocean worlds and their windows or their timelines for habitability. One compelling target that has been picked as an example target for purposes of this study is Orcus, just smaller than Pluto's largest moon, Charon. The presence of Orcus's moon, Vanth, also makes it an ideal candidate for filling in the large gaps in our understanding of collisional history and the formation of the solar system. This top view on the right is an actual Hubble Space Telescope view of Orcus and Vanth. Orcus, 910 kilometers in diameter. Vanth is about 490 or so kilometers in diameter, itself dwarf planet size. We'll talk more about that later. Some of you on this call may have been co-authors on a white paper that we submitted to another decadal survey, the Planetary Science Decadal Survey last year. And in this white paper, we outlined several big compelling questions for comparative planetology and ocean world science among dwarf planets. What fraction are geologically active? Is there ongoing plume, cryovolcanic, or tectonic activity? How are some dwarf planets able to remain active billions of years after their formation, as is the case for Pluto with its subsurface ocean and its active glaciation? What can the variability of geologic landforms and compositions tell us about the various formation processes and evolution of planets in the Kuiper Belt? What fraction likely have or once had liquid water? And if they had water, how long did it remain liquid before freezing? Was there a widespread process that extended the life of subsurface oceans, such as an ammoniated antifreeze? How is that related to a planet's window or timeline for habitability? Maybe they were habitable for the first billion years of solar system history and then became uninhabitable, perhaps due to thorough freezing. How do the atmospheres of dwarf planets interact with the solar wind or even the interstellar medium? And how does that interaction change based on the planet's position within or without the heliosphere? We don't understand at all space weathering from the interstellar medium. And finally, can dwarf planets be used as analogs to infer properties of dwarf exoplanets? We're a long ways, I think, from discovering dwarf exoplanets around other stars. But if they're the most common type of planet in our solar system, then they're probably the most common type of planet, not just in our galaxy, but the universe probably. So our exploration of Pluto, Triton, and Charon were just the beginning. Voyager 2 flew by Neptune and Triton on my 4th birthday in August of 1989. And I like to think NASA chose that date on purpose. Voyager 2, while it lacked an infrared spectrometer to show us Triton's surface composition, still did a marvelous job revealing the geologic diversity across Triton's surface. We saw a dwarf planet that got tidally reactivated when its giant planet host, Neptune, pulled it into a retrograde orbit and began squeezing it gravitationally. Voyager saw erupting geysers, showing that at least some geologic activity still occurs 5 billion kilometers from the sun. From Voyager's exploration of the Neptune-Triton system in 1989, fast forward to 2015, when New Horizons finally showed us the double planet of Pluto and Charon, which orbit around a point between them. Despite Charon and Pluto being so close to each other physically, each planet has tremendous geologic diversity across its own surface, between their two surfaces, and between them and Triton. Given so much diversity among the 3 Kuiper Belt dwarf planets we've seen up close so far, what do the surfaces look like on Quaoar, or Gong, or Orcus, or another of the 130 small Kuiper Belt planets? Inquiring minds want to know. Let's talk about the geology, geophysics, and composition of dwarf planets. The top 4 frames here tease at more of the geologic diversity across Charon, Triton, and Pluto. Foundering icebergs, 180 kilometers in diameter, arrested from sinking due to a quickly freezing Southern Ocean on Charon. Sooty geysers, sublimating cliffs, and potential spreading ridges on Triton. A sooty, tholin-covered band around the equator, a flowing nitrogen ice glacier, and spreading canyon-like grabens, cryovolcanic mounds, and a blue, stably stratified atmosphere on Pluto. Across the bottom, we see the relationship between temperature, size, and retained volatiles on small Kuiper Belt planets. The right side of the curve shows volatile retention, and the left side shows volatile loss. Now, while we may be tempted to think that volatiles necessarily make for more interesting geology and geophysical processes, interesting geology can still occur on volatile depleted planets, as proven by Charon. Now, even though a planetary flyby is very brief in time, measured in days and hours, the data collected are revolutionary for worlds that have never been visited before. To prove my point that single flybys of unexplored worlds can change our view overnight, and in so doing, I want to highlight that scientific value has nothing to do with how long it takes to acquire that knowledge. This view on the left shows our best view of Pluto from the Hubble Space Telescope prior to the reconnaissance of New Horizons in 2015. Literally overnight, or at least almost literally, our view of Pluto went from a fuzzy orb to a complex planet with cryovolcanic mounds, very interesting geology. And it took me several hours after first downloading this image to scrape my jaw off the floor after first seeing it. Now, where we go and what planets we observe it depends on which direction of the heliosphere we fly out of. And Elena did a great job covering some of those trades earlier on. But really, whatever flyout direction the heliophysics community wants to fly out, because this is a mission driven by heliophysics constraints, of course, it almost doesn't matter because planets and planetesimals are everywhere. So with 130 known dwarf planets and thousands more smaller planetesimals, just a slight tweaking of a heliophysics trajectory can allow a revolutionary flyby to occur. We've seen this plot before. Of course, warmer colors are faster flyout speeds on a latitude-longitude map of the solar system. It's hard to see, but I promise you different launch years are on the bottom of the screen here, driven by the position of Jupiter. Now, in our option A example, if we launched in 2036, we could fly by the dwarf planet Orcus. If we launched in 2037, we could fly by another smaller Kuiper Belt object. And if we launched in 2041, we could scooch this circle up just a little bit potentially and fly by Quaoar, itself an incredibly fascinating dwarf planet. Now, speaking of Jupiter driving which direction we fly out, as Interstellar Probe flies by Jupiter, we could conceivably do something like New Horizons did when it did its Jupiter gravity assist in 2007, and that is function as a science dress rehearsal for what we'd get to at a later Kuiper Belt object or dwarf planet. So New Horizons gravity assist in 2007 put it on course for Pluto while also speeding it up and shaving 3 years off the mission. Now, while hitting the gravitational bullseye is going to be the overriding concern for any spacecraft doing a Jupiter gravity assist, the potential for serendipitous science, or at least practicing the types of observations, getting familiar with the spacecraft's quirks would be important. Here we see on the left Europa rise over the limb of Jupiter. And on the right, we have an incredibly scientifically valuable view of Io's Tvashtar volcano erupting and sending a sulfurous plume high into space and then coming back down onto Io's surface. No other spacecraft has ever gotten a view this enticing of Io's volcanic active eruptions. As others have talked about early in here, we have a baseline snapshot of what the baseline heliophysics spacecraft would look like with, other than an ultraviolet imager for looking at the sky, there would be no remote sensing package on this. Now, with just a few trades, we could add eyes, if you will, to this spacecraft with an augmented payload. So keep in mind that we wanted to keep the mass to about 90 kilograms. These pie charts on the bottom show percentage of data returned, I believe. The heliophysics baseline is 87 kilograms and about 87 watts. And if we swap off the Lyman alpha instrument, which itself admittedly would be painful, and I know Elena is cringing at that concept, we would have the mass and power margin to add a flyby imaging camera that would have visible wavelengths in the visible and near infrared, as well as an infrared mapper for astrophysical considerations that I believe Mike Zemkov will speak to next, and they could be accommodated on the spacecraft here. Let's take a closer look at that. The visible near infrared camera would be sensitive to wavelengths from 0.4 to 3 microns. That would allow us to see absorption bands from different organics on planetary surfaces. It would have a very small 10 microradian or thereabouts instantaneous field of view. Importantly, though, it would require the spacecraft to be 3-axis stabilized and not simply a sun-pointed spinner, at least for the planetary encounter. We've used New Horizons Ralph instrument. It's literally a camera named Ralph that has similar characteristics. And I believe Mike Zemkov will speak more to the infrared mapper that would see much further into the infrared, albeit with slightly coarser resolution. Now, keep in mind, of course, we would have to transition from a spin-stabilized spacecraft briefly to a 3-axis control spacecraft for this time. There's also the potential for dwarf planet atmospheric science. Shown here in visible light is the view of Pluto's atmosphere as New Horizons flew into that planet's shadow from the sun. It's a beautiful blue atmosphere. On the right, you can see this incredibly stably stratified atmosphere itself illuminating some of the terrain toward the bottom. Now, unfortunately, in our augmented design, we were not able to include a UV imaging spectrometer and stay within the mass and power constraints for the planetary augmentation. However, because we're simply presenting a menu, a future science and technology definition team, STDT, could choose, for example, to combine the capabilities of the planetary visible infrared and the astrophysical infrared mapper into one instrument and add a UV imaging spectrometer. An instrument like the New Horizons or Rosetta Alice UV imaging spectrometer serves as a useful example. Such an instrument, for example, could detect a 10 nanobar, 50 Kelvin methane atmosphere, giving a surface density of 10 to the 12 molecules per cubic centimeter, easily within the detection limit by several orders of magnitude for an Alice-like instrument. So we could still do compelling dwarf planet atmospheric science if we have reason to suspect that the target dwarf planet may have an atmosphere. We believe that many dwarf planets simply lack atmospheres, or at least detectable atmospheres. Let's talk a little bit about the ConOps for dwarf planet flyby. I'm going to try to get this animation to play while I speak to it. We would transition from spin stabilized to 3-axis control, probably several days to weeks before closest approach. On approach, we would conduct OpNav or optical navigation to make sure that we not only nailed our flyby distance and position, but also that we knew the precise timing of when closest approach would happen, which is necessary for updating spacecraft pointing for acquiring images. We would target a flyby distance of 5,000 to 40,000 kilometers from the dwarf planet's surface, which is very comparable to the flyby distances that Voyager and New Horizons did of their various planetary targets. Of course, we'll be looking at speeds in excess of about 7 AU per year. That's in comparison to New Horizons' 3 AU per year, or Voyager 1's about 3.6 AU per year. Now, most dwarf planets have spins significantly faster than Pluto, several tens of hours versus over 6 days. That would allow us to not only view the closest approach hemisphere, but also to get rather good maybe a few tens of kilometers per pixels resolution on the non-encounter hemisphere before closest approach. New Horizons saw the non-encounter hemisphere 3 days, half a Pluto day, before closest approach. And while it has better images of Pluto's non-encounter hemisphere than anything taken from Earth, it's still rather coarse. We'd be looking to get ground resolutions better than 1 kilometer per pixel, which is necessary for observing geologic landforms and interpreting it. And what I've shown here in this animation is the type of imaging that could occur. We used Charon as a stand-in example because Charon is very typical in size to Orcus, Quaoar, Gong, and many other dwarf planets. And as we get closer, we'd have we'd have a smaller field of view, smaller footprint on the planet, but higher resolution. And then as we got to closest approach, we would get this blue high resolution noodle and could even do other spacecraft slews and scans across the surface to perhaps acquire targeted imaging of maybe some interesting areas. So this would be eminently doable. Next. Okay, so we've used Orcus and Vanth as our example target binary planet. As I mentioned earlier, Orcus is 910 kilometers in diameter, and the system will be 48 AU from Earth in 2036. By comparison, Arrokoth, that small planetesimal, was 45 AU when New Horizons flew by on New Year's Day 2019. So we know how to operate. We have experience operating in this region of the solar system. Orcus is in a 3-to-2 orbit resonance with Neptune. It orbits the sun 3 times for every 2 times that Neptune orbits, which is the same as Pluto. It's in the same resonance as Pluto is, but it's also anti-aligned with regards to when it is at closest approach to the sun versus Pluto. Orcus has an ammoniated surface, potentially ocean antifreeze, which could hint at cryovolcanism. It has a very large moon, Vanth, half its diameter. They orbit a point in between, just like Pluto and Charon orbit a point in between. It's another binary planet. We could have a possible launch in 2036. Now, if you've been paying attention for the last several years with Interstellar Probe, we've previously talked about Quaoar and Gong as example dwarf planets. But again, the position of Jupiter dictates where we can go. Now, if having a full planetary augmented payload is too much to swallow for the heliospheric community and it's too many compromises, we could still get nearly as good planetary science with a sun-pointed spinner that never points around. This could be accomplished with a nose camera on what I've been nicknaming the Helio Plus baseline, a camera that only ever
Thank you again,
stares.
Phil. Appreciate all your support through this program.
We would only ever stare straight ahead, and it would capture images as the spacecraft approached the dwarf planet, but not at closest approach. This picture of Pluto is similar to what such a nose cam could get from 3 times further away New Horizons closest approach distance, and it's still better than a kilometer per pixel. So we could also have a wide angle look back camera for exoplanet type science, exoplanet analog science, where we get unresolved views of giant planets using them as exoplanet analogs. As interstellar probes leaves the solar system, it'll have a unique view of the giant planets, seeing them as crescents, which are views impossible to get from in the solar system. Seeing how the light, even on 1 pixel, changes as a function of crescent size or phase angle, and also as the planet rotates, will allow exoplanet scientists to better understand the unresolved views they have of worlds beyond our own solar system. And this could be a very small, low mass, 3 or 4 color camera accommodated on perhaps even the high gain antenna of a heliophysics baseline mission. So in summary, lots of reconnaissance potential for 130 dwarf planets. Planetary flybys are revolutionary. Orcus and Vanth are compelling targets, and a fully augmented payload with a visible infrared camera or the Helio Plus nose cam could enable geoscience exploration of dwarf planets. And so I say, let's get more dwarf planets in our rear view mirror. Thank you.
Thank you, Kirby. Fantastic. We have one quick question here. How close do we expect to get to Jupiter with the flyby? And I know that the answer is the trajectories are planned at 1.05 Jupiter radii from the center of Jupiter. So very close to the cloud tops. I believe that was the orbit insertion perijove altitude at orbit insertion for Juno. So it's not outside of the normal for such missions. Yes, wow, says Tony Freeman in the question and answer. It seems very close, but it's definitely within the ability for us to control the spacecraft's flyby and position in space. So, and Marshall asks, would you try for radio occultation at a TNO flyby? That'd be great, but I think that working out the geometry on that would be only if accidentally the KBO that we fly by has its own path, its own trajectory allows that to happen. I don't think we can do enough with the fuel on board, given the incredibly high outbound speeds that we have to make that happen. But that is certainly something we could start to track. That's an interesting idea. So thank you, Kirby.